Okay, this lesson is about flight instruments. These are instruments we use to control the aircraft. We're going to divide this into four parts. The first part will be an introduction to flight instruments plus an introduction to what's something called the pitot system and the airspeed indicator. Then we're going to learn about the altimeter and the vertical speed indicator in the second part. In the third part, we're going to learn about the vacuum system, which includes the attitude indicator, the heading indicator, and the turn coordinator. And then we're going to learn about the compass, the magnetic compass. So we're going to divide those into four parts. So make sure you've got your packets ready to go. And we will get through this one chunk at a time. So here we go. All right, flight instruments. We're still talking about aircraft in this part of our lesson here. And you should know that flight instruments are instruments we can use to maneuver the aircraft. Make sure you're following along with your notes as we go here. We're going to bust through a lot of concepts here. These are the seven instruments we're going to be talking about: the airspeed indicator, the altimeter, the vertical speed indicator, the attitude indicator, the turn coordinator, the heading indicator, and the magnetic compass. And here's the six in their gauge form. Now, there's all kinds of different ways these can be represented in different kinds of airplanes, but essentially, no matter how they're represented, whether an actual physical gauge like this or digitally, they do the same thing. This is what we call a glass panel or an integrated flight deck, and this it has the same things. We have an attitude indicator and here in the middle. We've got an airspeed indicator, altimeter, we've got a heading indicator, and we're going to learn about these as we go. And this is the magnetic compass. It literally just hangs in the plane somewhere or is on the dash, and you can read it. It works off a magnet floating in a type of non-freezing liquid. All right, let's start with the pitot instruments. Pitot instruments depend on changing air pressure. Now, so you need to know a little something about air pressure. And that's as we go up in the atmosphere, there's less air pressure. So engineers and designers and scientists years ago figured out like, hey, if we could have gauges based on that, we could know things like how high above the earth we are. We could also know about air pressure coming into like a port to tell us how fast we're going, things like that. So air pressure is measured in inches of mercury or millibars. For example, you may have 30.12 inches of mercury for air pressure, or you may have something like 1020 millibars. I think millibars is more of a metric system measurement. Here in the US, we use this kind of altimeter setting here. Standard atmospheric conditions. This is one of those facts you just have to memorize as a pilot. It comes up on a lot of different test questions, and you use this to convert things from like regular indicated altitude to pressure altitude and things like that. But what they say is that a standard day is 29.92 inches of mercury and 15 degrees Celsius or 59 degrees Fahrenheit at sea level. Now that's what they consider to be the average or the mean. And I don't know if it's based off years of research or whatever. I don't know where they came up with those numbers necessarily. However, I do know that there's a lot of test questions based around that. So please memorize that bullet point right there. 29.92 inches of mercury, 15 degrees Celsius or 59 degrees Fahrenheit at sea level. Make sure you got that one memorized. In a standard day, the pressure falls by approximately 1 inch of mercury for each 1,000 feet of altitude gained. This is another one you want to memorize. So every time you go up in the atmosphere 1,000 feet with standard, on a standard day they call it, you'll lose 1 inch of pressure on that mercury gauge, that barometer, for every 1,000 feet you go up. So theoretically, if you went up 6,000 feet, pressure would be 6 inches lower on the scale than it would be at sea level or wherever you started. So that's another FAA definition. Just memorize it, please. Alrighty, let's talk about this system. This is called the pitot system. The pitot system, and it's got some different parts. This part is outside the plane. This part is outside the plane, and then this piping is going through the plumbing here is going through the plane, and then we have these gauges we might see on the flight deck. So let's start with this thing. This thing is called the pitot tube. The pitot tube. Then we have the airspeed indicator, the altimeter, the vertical speed indicator, and the static port. And those are the major components of the pitot static system. We also have lines that are carrying just air from those ports to the gauges. Alrighty, this is what an airspeed indicator might look like. Now the colors will be different depending on the airplane you're flying because different airplanes have different limits. But what we're going to talk about here is how it works. Number one, the airspeed indicator uses ram air pressure to measure indicated airspeed. It uses ram air pressure to measure indicated airspeed. It's the only instrument that uses the pitot tube in most general aviation airplanes. It uses the static ports as well. So this is the pitot tube. Air comes in there through the airlines to the airspeed indicator, and then it's also using the static port to just fill it with air. And essentially what it does is it pushes on these things in there. It's called a metal diaphragm, and it pushes on it, and as it does, it moves linkages left and right. Let's take a look at how that actually looks here. So you have something like this. You have ram air coming in by the wing somewhere, or maybe on the nose of the plane, coming in the pitot tube, pushing on this diaphragm, moving these linkages, which then move the little needle on the front. The static airline just fills it with air, and it basically is measuring the difference between the ram air pressure and the outside air pressure. We want to make sure that that line stays open because we need to know the actual outside air pressure so we can measure the same air versus the same air, but this is moving fast, so this tells us how fast we're moving. You can go out and take an air compressor and hook it up to a pitot tube with the airplane not moving, turn it on, spray air into it, and it would move. It would move because it's based on air pressure. It's not really measuring the speed of the plane exactly, like how fast the wheels are turning or anything. It's measuring how much air is pushed into that pitot tube. Now there's lots of different speeds that are measured on here. So let's talk about some of those. First one is the VSO. It's the lower end of the white arc. And this is what the stall speed in the landing configuration. The plane should stop flying right about there. Now we're going to talk more about that in a little while. One thing you should know about VSO though is that it's at max gross weight. So your stall speed could slow down. So if you don't know what a stall is, don't worry. But basically, that's when the wing kind of quits flying. We'll talk more about that if we haven't yet in class already later in a lesson. But basically, that's where the plane's going to quit flying, is right about that speed. It doesn't have enough air over the wings to fly. VSO, stall speed in the landing configuration. So this is if planes have landing gear, they need to be out and down. The flaps need to be in the landing configuration, etc. And then we have VS1. It's the lower end of the green arc. And when I say lower end, even though it looks like it's higher up on the screen than this looks lower than that. We're talking about speeds. It's the lower speed on the green arc. And it's usually a stall speed in a specified configuration. So it'll also stall here, but it's specified by the manufacturer. And usually it just means like the clean or no flaps down kind of configuration. VS1. Then we have the wide arc. And the wide arc, you can fly with flaps fully extended at this speed, meaning you won't damage the flaps if you deploy them all at this speed. So at 100 knots in this plane, if you deployed the flaps, you would be okay. You can use the flaps anywhere in this wide arc. You can use them at slower speeds too. It won't hurt them, but you could deploy them in this wide arc fully. And that speed that you have to be at is called VFE, velocity flight flap extension. This is the maximum speed to extend flaps fully. It's the upper end of the wide arc, we call it. Then we have this green arc. The green arc is for normal operations. This is where you're kind of cruising around. You can do lots of different things in this. Depends on what maneuvers you're doing, but typically green arc is just kind of a nice safe range for cruise flight. Then we have VNO. This is the maximum speed for normal operations. I like to think of it as like the max speed in bumpy air. It's the upper end of the green arc. Okay, so if it's getting turbulent, you want to stay down here in the green arc. There's even another speed that we're going to talk about that maybe you want to be less than if it's really turbulent. Then the yellow arc is just smooth operations only. So only when you're in smooth air should you be in the yellow arc. You can do damage to the plane by forcing it into rough air if you're in this yellow arc, if you're like in a dive or something. V&E is the never exceed. Your wings could fall off, so let's not exceed that. Let's not exceed that one. Of course, it could bend the frame. It could do other things too. But V&E is the never exceed. It's the maximum speed for that aircraft. Now, there's 4 types of airspeed we're going to talk about. The one we've been talking about looking at the airspeed indicator is indicated airspeed. And the reason why you need to know all of these is one relates to another. You have to know indicated airspeed to figure out calibrated airspeed. You have to know calibrated airspeed to figure out true airspeed. And you have to know true airspeed to figure out something called ground speed. So let's talk about each one of these. First of all, indicated airspeed is read right off of the airspeed indicator. So this one's going 110, so the airspeed, indicated airspeed, or KIAS or IAS, knots. We measure them in knots, indicated airspeed or indicated airspeed. Maybe I didn't talk about that too much. We use knots, nautical miles per hour. It's this different than the speed in your car. In a car, when you're driving, you're using statute miles per hour. We just call it miles per hour when we're driving. Well, in an aircraft, we call it knots. How many knots per hour are we going? How many nautical miles per hour are we going? The conversion between a nautical mile and a statute mile is about 1.13, I think. So, all right. So we just look at a gauge, we read indicated airspeed. So what's calibrated airspeed? Well, this is indicated airspeed calibrated for installment error. So there might be a little bit of error. So inside the operating handbook for a plane, it'll say, hey, your indicated airspeed is 90, but really your calibrated airspeed is 89. So really you're probably going more like 89 than 90. You can see looking at this chart, there's not a huge difference. The biggest difference is about 2 knots. 130 versus 128 or 120 versus 118. Really not a huge difference. It looks like in kind of this mid-range they're exactly the same, but when you get a little slow, well, here's 5 knots difference, so maybe there is a big difference. But that way you can kind of use that calibrated airspeed. And if you remember, calibrated airspeed is used to figure out true airspeed, and true airspeed is actually very handy to use as well. So let's learn about true airspeed. True airspeed, or knots true airspeed, KTAS. This is calibrated airspeed corrected for altitude and temperature. It gets faster with altitude. So how much faster? About 2 knots per 1,000 feet, roughly, depending on the plane. So if you're 10,000 feet in the air, your true airspeed is actually about 20 knots faster than you would be at sea level. So 100 knots indicated at sea level is about 120 true airspeed at 10,000 feet. So that's 20 knots difference. It's basically how fast you're moving through the air. It's really kind of a hard concept to understand. You don't need to know a ton about it. What you need to know is how to figure it out. So when we get to calculations, we have a whole lesson on calculations. We'll show you how to use that and how to figure that out, because you really need true airspeed to figure out ground speed. And ground speed is important. It's very, very, very important. Ground speed is just how fast you're moving across the earth. So for example, you're flying at 10,500 feet mean sea level. We haven't learned that term yet, but that's above the ground. 10,000 above sea level, 10,000 feet above sea level, with an indicated airspeed of 105 knots and a 16-knot tailwind. How fast are you going? So this is a good question. I get this question a lot. What kind of planes do you fly? Oh, I fly, Skyhawks. Well, how fast do they go? Well, are they talking about, they want to know indicated? Well, they cruise about 105 indicated. Oh, 105 miles an hour? No, 105 knots. Well, what is that? Well, it's like, 113 miles an hour or whatever. I don't know. And then they're like, but what they really want to know is how fast can you get from one place to another? Well, do I have a 20-knot tailwind? Do I have a 15-knot headwind? What does that mean? Plus, what altitude am I flying at? If I'm flying at, like I said, 10,000 feet, I'm actually going more like 125, 130 true airspeed, which means my ground speed's a lot faster as well. And so let's figure this out really quickly. Let's do an example here. How fast are you going? Well, indicated off the gauge, 105. Calibrated, well, about 2 knots slower, so more like 107. or 104, sorry. Did I figure out? Oh yeah, sorry, 104. And then true airspeed, 2 knots per 1,000 feet, so about 124. It's true, okay? And then you take a 16-knot tailwind, you'll actually add that tailwind to that. My ground speed is more like 140, okay? Because I got a tailwind pushing me along there. So 140, that's my ground speed. Now, if I had a headwind, we would be subtracting that from that true airspeed to figure out our ground speed. And that's important because we want to know how long it's going to take us to get somewhere, because we burn gallons per hour, right? Our fuel is dependent upon how long we're going to be in the air. And if I've got a 20-knot headwind, I'm going to need more fuel because it's going to take me longer to get there. If I got a 20-knot tailwind, it's going to need less fuel. It's going to take me to get there. So, you know, we really want to know ground speed. Plus, it's going to let us know how long I'm going to be sitting in this plane going somewhere. Here's some more airspeeds for you. Ready? These are not marked on many airspeed indicators. Number one, VA maneuvering speed. This is when you can go full deflection of any flight control surface because of the risk of damage to the aircraft structure. When in moderate turbulence, you should slow to this speed, and it decreases with weight. I'm going to talk more about this one in class. This is one that's kind of tough to get from a video, so I'm going to talk more about that one in class. Then we have something called VX. This is the best angle of climb speed. Best angle of climb. Okay? Use this when you have to climb in a short distance. And then we have VY, which is the best rate of climb speed. Use this for best climb in a certain amount of time, not distance. I use VY usually when I'm climbing out. So how am I going to remember these? Well, we'll watch a video in class about it. But to tell you really quickly about VX and VY, if you've got a runway and you've got a tree at the end of the runway and you're taking off and you want to clear that tree, you're probably going to use VX because you need to climb in a certain amount of distance. If you want to just climb over a certain amount of time, I'm going to climb for 30 minutes, I would use VY. And basically you just pitch full power and you use your pitch to make sure that airspeed indicator points right at that. In the Skyhawk, VY is like 72 knots and VX I think is like 65 or something. It depends on the model of Skyhawk. But that's the difference, is about 7 knots. But one will get you, if you timed it, one would get you a lot more climb over a certain amount of time. If you were going over distance, like you've got an obstacle you've got to get over, VX is your best angle of climb to get over that. Now, how do I remember those two? I keep them separate. I just remember that the X and VX has more angles in it than Y and VY. It's the best angle of climb. It's got more angles than that X and the Y. I know it seems silly, but that's how I remembered it. All right, we'll watch that video in class. Here we go. So Pitot tube to the pressure chamber, Pitot heater switch, airspeed indicator, vertical speed. This is just another drawing of the Pitot static system, because we're going to talk about the altimeter and vertical speed indicator next. One thing that says right here, Pitot heater switch, there's actually Pitot heat. You can turn the switch off and on, and it'll melt any ice off this Pitot tube if you want. You can also, if you have a static port blockage, you can pull this static source and it'll bypass this and bring an alternate static source from inside the flight deck to these instruments as well. So if this gets blocked in flight, you can have an alternate source. If this gets blocked in flight, you can try to burn it off using the Pitot heat in that. All right, that's the end of part one. The next part, we're going to talk about altimeters. Still talking about the Pitot static system, but we'll talk about altimeters.